Now you know everything you need to know about drawing Lewis structures. Next, we're going to take those flat Lewis structures and turn them into three-dimensional shapes. Even though we generally draw our Lewis structures very boxy, that doesn't mean the molecule actually looks like that. The Lewis structures are just good at telling us which atoms are connected to which other atoms, and where the electrons are assigned. We need to know other information like bond angles to know the true shape of the molecule. To figure out the 3D shapes of molecules, we are going to use a theory called VSEPR Theory, which stands for Valence Shell Electron Pair Repulsion Theory. It is valence shell because we are dealing with valence electrons. Electron pair repulsion refers to the fact that electrons want to get as far away from each other as possible. Remember, like repels like. That push from the electrons to get as far apart as possible makes the 3D shape of the molecule. To figure out the molecule's shape, the first thing we are going to need to know is how many electron domains are on the central atom. Electron domains are regions on the central atom that contain electrons. I like to think of this like a floral arrangement. There's often a styrofoam ball with flowers sticking into it at different angles. The styrofoam ball is the central atom, and how things stick into it determines the shape of the arrangement. Electron domains, which are regions on the central atom that contain electrons, can be lone pairs, single bonds, double bonds, or triple bonds. Each counts as one domain. Basically, ask yourselves the question, are any electrons on this part of the central atom? If yes, then it is a domain. For example, in carbon dioxide, there are 2 double bonds on the central atom. Each counts as one domain, so that molecule has 2 domains. In ozone, the central oxygen has 1 single bond, 1 double bond, and 1 lone pair. Each counts as a domain, so there are 3 domains on the central oxygen atom. The ammonia molecule has 3 single bonds and 1 lone pair. Each counts as one domain, so there are 4 domains on the central nitrogen atom. The number of domains determines the type of electron domain geometry. When there are 2 domains on the central atom, the electron domain geometry is linear. Think of it like 2 balloons tied together. They want to be as far apart from each other as they can, so they push each other into a linear position. When there are 3 domains on the central atom, the molecule will have a trigonal planar electron domain geometry. Tri means 3, and planar refers to the fact that the 3 domains are all in a flat plane with each other. They still push each other as far apart as possible. 4 domains is when we really start getting into 3-dimensional shapes. When there are 4 domains, a plane is no longer able to get the domains as far apart as possible. Instead, they form a tetrahedral electron domain geometry. Tetra means 4, so if this were a geometric solid, it would have 4 surfaces. If any of you play role-playing games like Dungeons & Dragons, it would be like the D4 die. In other words, a pyramid. It has 4 sides and 4 corners. In our molecules, the electron domains would be pointing towards the corners. 5 domains is trigonal bipyramidal electron domain geometry. Try to picture 2 pyramids stacked on top of each other. One pyramid is pointing up, and the other pyramid is pointing down. The bases of each pyramid, which are touching each other, have 3 corners. The 3 corners forming the base of both pyramids is the trigonal part of the name. Bipyramidal refers to the 2 pyramids. Again, the electron domains are pointing toward the corners of the pyramid shapes. 6 domains is octahedral electron domain geometry. You may be confused at first because octa means 8, but the octahedral is referring to the shape of the geometric solid. If this were a geometric solid, it would have 8 sides, like a D8 die in Dungeons & Dragons. It would only have 6 corners, though, and you can think of the 6 electron domains as pointing towards one of the 6 corners. The octahedral geometry is similar to trigonal bipyramidal in that there is a plane in the center, with a domain pointing up and a domain pointing down. In the case of trigonal bipyramidal, the plane in the center has 3 domains. For octahedral, the center has 4 domains, all in a plane. So far, you should be able to draw a correct Lewis structure, count the number of domains on the central atom, and from that number of domains, pick which of the 5 electron domain geometries the molecule would have. Each electron domain geometry also has a corresponding bond angle. The bond angle for the linear electron domain geometry is 180 degrees. Since the atoms are all in a plane, you can think of it like a circle. The atoms cut the circle in half, so 360 divided by 2 gives us 180 degrees. The bond angle for trigonal planar is 120 degrees. Again, the atoms are all in a plane, but it is cutting the circle into thirds. 360 divided by 3 is 120 degrees. The bond angle for tetrahedral is 109.5 degrees. You would need to do trigonometry to figure this out, or just memorize it. There are actually 2 main bond angles for trigonal bipyramidal, 90 degrees and 120 degrees. The 120 degree angles are between the 3 domains in the central plane. This angle is just like the trigonal planar electron domain geometry, where we divide the circle into 3 parts. The 90 degree angles are because the other domains are perpendicular to the plane. We will talk a little more about this on the next slide. For thoroughness, and because WebAssign will ask you about it, there is also a 180 degree angle from the top domain to the bottom domain. They make a straight line. The main bond angle for octahedral electron domain geometry is 90 degrees. 4 domains are in a plane, so 360 divided by 4 gives us 90. The other 2 domains are perpendicular, so that angle is also 90 degrees. Again, for thoroughness, there would also be a 180 degree angle from one domain to the domain straight across from it. Trigonal bipyramidal molecules have 2 different bond angles and 2 different types of positions. There are 3 equatorial positions in a plane around the middle. They have the 120 degree angles between them. You can think of how the equator goes around the center of the Earth. The axial positions are above and below the plane, perpendicular to it, which is why there are 90 degree angles. You can think of the axis that the Earth spins around.